Okay, so what we're doing here is a little bit of recreational programming, likely mostly recreational yapping. Um, this will be our first stream. I suppose it's really the second stream, but the first one didn't go so well when we tried multi-streaming to both YouTube and Twitch. So the idea here is that we will do better using a service to repeat our streaming, which seems to be working right now. What I'm trying to do right now is set up these chats and OBS and everything on one screen on my laptop that I'm using for streaming. Yes, no, maybe. And since this is my first time really doing this kind of thing, we're going to be in full on janky land. Luckily, nobody is probably watching this, so that's great. Let's see, can we move this over so he takes the whole panel? Yes, we can. All right. You got to give it to Windows. So we're finally sort of figuring out how to do uh, split panels or tiling for Windows. Uh, all right. Yeah, I think we're kind of set up right now. This is not going to probably go great, but let's give it a try. So, what we're going to do today is a hopefully slightly shorter stream where we're going to go over a little recreational programming project that I've already started on. You can see it right here. We're calling it Snake Toy LM. That's called LM for language mess. Because what we're going to be working on is a um, sort of a programming language written in Python. We'll get into why Python, but it's a toy programming language, so it's a toy programming language in a toy programming language, and it's a little bit of a programming language and a programming language framework, right? So maybe like it would let us define more than one programming language, but for right now, we're just kind of trying to get like a proof of concept going. And the idea here is that we'll be able to then compile this programming language. Well, first we'll try to get it like a basic version of it working in a as an interpreter, but then we want to compile it down to some other targets. And the reason for that is that some of those other targets are going to be these virtual machines, uh, or I suppose different architectures that are Snake VM, Snake Toy VM virtual machine supports. And so I guess that leads us into what the heck is Snake Toy VM. Well, that's another recreational programming project that me and a friend of mine worked on. And as you can tell here by reading this description, it is a generalized toy virtual machine, toy being keyword here, right? So, like, we're writing a virtual machine, an emulator in C Python, Python, like the default traditional Python interpreter being C Python, and that itself is already a virtual machine. It's stack-based virtual machine. So we're implementing a virtual machine in a virtual machine, right? So like this is not something that you could possibly use in any kind of uh, useful uh, performance performance optimized. I hesitate to even say optimized way, right? This is again a toy. What we have here is a GUI that also has a bit of a infrastructure framework, if you will, where you can define assemblers and assembler languages. Those assembler languages can then be compiled down to a virtual machine that you also define to be associated with this assembler that you defined. And the code that you write can be executed. And then you can view the effects that your program is having on the registers and the memory, uh, through the GUI, right? So this allows you to implement different architectures and then run them on the uh, define the assemblers for this architectures as well, and then run uh, their machine code on the architectures, the virtual machines that you defined. And the ones that we've defined so far are this toy virtual machine, which is just a completely made up virtual machine and an associated assembler that I made up as I was writing this whole project. So, just completely kind of um, completely made up and also completely sort of like emergent architecture that came along as I was writing the infrastructure and the code to like accomplish all of this. Also, my buddy implemented Kawayan. Shout out to him. Wrote a brainfuck uh, virtual machine, so it's able to execute like it's able to compile down brainfuck to uh, the bytecode to run on the brainfuck virtual machine that he implemented, which is pretty sweet. I also implemented um, a very basic. This is actually like a real architecture that's defined. It's F4, which is a MISC, which is like a I forget exactly what it's what MISC stands for. You can Google this, but it is a minimal uh, instruction set, right? So the idea is that these are um, processor architectures that are designed to have a fully operational Turing machine, modern day classic architecture processor, but with the absolutely minimal instruction set possible. Like, so it's like even more minimal than RISC, which is like the reduced instruction set uh, architectures. I suppose we we just put it here. Oh, I guess Google doesn't believe that we're not a robot since we're MISC CPU architecture. Yes, minimal instruction set computer. And F4 is one of these architectures that's super, super simple. There's a specification for it, and I implemented it for our virtual machine in Python. So going back to what we're doing here with Snake Toy LM, which I haven't pushed any of the code up there, but we'll push it up to this public repo shortly, is we want to have high level language that we've defined ourselves that it's able to be compiled down to some of these architectures, maybe eventually. Or maybe we can even have it compiling down to Python bytecode and do some other fun stuff. But the idea is that we're going to implement all of those components that go into writing a language in Python as a fun recreational program exercise, and also uh, maybe some of this stuff can be instructional, right? The idea here is that like we're re-implementing things that are fundamental to computers and computer science. We're not implementing them in a great way, and we're not implementing any. We're not creating any useful implementations of them. But like, who cares? There's plenty of really, really smart people that have, created a lot of useful implementations of these things, right? So as opposed to us attempting to implement LLVM, which inevitably I would fail. Creating something as useful as that, we can do a really botched version of that in Python, but that maybe illustrates the basic components of what uh, a computer language creation infrastructure has or provides, and the methodologies for doing that, and what computer languages are and how they're implemented. Uh, very basic and hacky way. But either way, it should be fun for me. And the idea why we're doing this is because I suppose these are things that are fun to me and I do as a hobby, as one of my many hobbies. I'm professionally have done software engineering, programming, whatever you call it, for many years, and I grew up um, at a time in Eastern Europe when computers were coming up in the 90s, and that was a fun thing that a lot of me and my friends did. Uh, Again, as a favorite pastime of ours, and somehow decades later, it's still a favorite pastime of mine. So this streaming thing seemed like fun. Like potentially getting some people on stream eventually if anybody ever ends up watching some of these. I'm going to put them on YouTube where, potentially maybe some people can see them, and then maybe eventually a couple of people maybe even might join the streams. Not likely, but if they did, that would be kind of a fun thing, and then it's almost like coding with your friends, or at least that's the idea. It seemed like a fun thing for me to try, so I'm going to give it a try, and we'll see if we end up continuing this or not, or what happens. But yeah, I guess that's my whole spiel on what we're doing here and why we're doing it. Um, let's, I guess, take a quick look into what we already have, and we'll sort of go back and forth between this and my ASCII diagram board, and we'll talk about some programming languages and how, I guess, computers work on some high level and things like that. So this stream will probably mostly be like yapping and talking about things that are already implemented in this uh, toy project that we're working on here, the Snake Toy LM or language mess. Um, and then eventually, hopefully next week or sometime, we can have like a follow up session and we can implement some things and fix some of the broken things that currently exist in the state of this project, because I sort of left it as is with the idea that I wanted to stream some of this, and then life gets in the way. So finally, we're hopefully getting to it and at least doing this like initial introductory session and figuring out whatever streaming problems we might have and so on. Okay, so uh, what we have here, actually, I think I have a good way to overview this. Oh, there we go, yeah. So we'll just list the project really quickly. Um, we have our basic Python project that is attempting to implement a lexer or a tokenizer, uh, and then a parser, and currently an interpreter for that parser, right? And the lexer, the parser, and the interpreter were sort of kind of implementing in a modular way so that we can define different language syntaxes, right? And also uh, potentially, right, like also not just be able to like interpret stuff, but compile them down. So we implement like a compiler, or we implement the the, the framework, the infrastructure, the scaffolding to create interpreters and then compilers, and we'll work on some sort of made up high level language, or maybe we implement some sort of very simple existing high level language or something. Where we are right now is that we are more or less parsing expressions, not fully, because we're not supporting all of uh, possible operators with expressions. I think right now we just have like multiplication and addition. Um, and also, I started implementing statements and blocks or compound statements, depending on different languages and different, I guess, schools of programming language design use uh, different jargon, different terminology for these things. And I suppose we should get into what some of these things are, but we can take just a quick look here on what we have built so far. And because it's in a little bit of a broken state, we're probably not going to uh, be able to, I guess, see very much, but let's just go ahead and run it. So this is our REPL, right? So we have like an interactive REPL that allows us to like define some stuff. So it's kind of like, you think of it like the Python REPL. When you type in Python, it puts you in the interactive environment, right? You're able to write programming language statements in that case Python, but in our case it's like our made up programming language that we're sort of defining along as we're defining the actual scaffolding to define lexers and parsers and all of those things. Uh, yeah, these are a lot of ahs and ums, but I'm working through this whole streaming thing. So luckily, nobody will probably watch this even once it's on YouTube, so we don't have to worry about that too much. But what we can do here is we can say, like, for example, 1 plus 1 And in this case, well, first of all, we'll get into why I'm doing like a weird thing where like there's spaces between the plus and the one and everything else. This has to do with our very like primitive way that we're parsing or we're lexing or tokenizing the text. But again, we should probably go over what all of those things mean first. But either way, 1+1, we can see that right here to the terminal, we get dumped out that we have these tokens. And this text here that we've written 1+1 has been turned into an int literal 1, right? So this is the way that our repo or our interpreter or whatever you want to call this has understood what we have typed in there right now is that it thinks that we're telling it, hey, we're going to give you a number. This number is going to be 1. We want you to do an operation with this number. And it's the operation is the plus operation. And we want you to plus it or add it to another literal who's always also going to be an integer number, and that number is 1, right? And for right now, what we've dumped here is what we have, how the stacks have been converted into tokens. Later on, those tokens are converted into well, depends. There's different approaches on how these tokens are then turned into something that the computer can execute. But very commonly, one of the first steps is to then take those tokens and turn them into some sort of a syntax tree. And the syntax tree, a tree is a data structure, and this specific data structure, this specific tree is meant to represent the operations in the it represents what we want to the operations that we want to perform in this tree data structure format. I'm not doing a great job here, but hopefully we can get better at this, and we can get rid of some of these ums and ums and pauses where I'm thinking and trying to present this in a not super verbose way, but maybe informative way, which I'm totally failing at right now, but let's keep on going here. All right. So we can see this. I think I have implemented, I think this still works. So this /show is a command that we've implemented in our very rudimentary REPL that can show us what our REPL has parsed or understood from what the statements that we've given it. Right now, we're just giving it 1+1, and we're able to see that initially turned that into tokens, but then it's actually gone ahead and turned that into a abstract syntax tree. And this really not very readable structure that you see here is the nested objects that represent this abstract syntax tree of what we're like, what the interpreter thinks that we want to accomplish by what we've given it. So in this case, we're starting at the node of the tree, the root of the tree, which is the first node. In computer science, the trees are always inverted, meaning that if you imagine a tree starts with a trunk or like the roots, and then it starts turning into many little branches and branches and branches, and at the end of those branches, you have leaves, right? Well, it's a similar thing in the data structure in computer science that's called a tree, but it's kind of like inverted because really the way we often represent it is we start with the root of the tree at the top, but again, this is representation. The way that it's actually represented in memory, it has nothing to do with our analogy of a tree. But nevertheless, here this is one representation. This is a nested representation of how you can represent a tree structure, really any kind of graph, and it's you have some sort of object, and that object contains the objects that are its subnodes. So in this case, we start with this. I don't know how clear this is, but we're just going to go with it. We're starting with the root of this tree, and the first subnode to the root is a statement, right? So our interpreter has understood that, hey, we want to execute some sort of statement. This first statement is binary operation, meaning that it's an operation that's going to be involving two other nodes, right? In this case, the binary operation is addition or plus, right? So our binary operation in this case would be adding 1 to 1, right? And the way that, yeah, computers function in the way that a lot of the, how these things are represented in programming languages, they're very commonly represented as these binary operations. So if you have an expression, like a mathematical expression that's 1 plus 1 plus 1 plus 1 plus 1 plus 1, you're going to evaluate it as this, you're going to evaluate it as binary expressions, one after the other, meaning that you're going to add the two ones first, and then you're going to add the extra one to the result of those first two ones. Um, and exactly the order in which you evaluate this expression, I guess we can maybe let's see. Can we so if we had 1 plus 1, right? But what if we wanted to do, again, I'm doing kind of a poor job of explaining this. Uh, we're talking about the order of operations. Just like in mathematics, there's an order of operations. In the same way, when programming languages are executing or attempting to evaluate an expression, a mathematical expression, they're going to take into account the order of operations. But in programming languages, there is more than just mathematical operations that can happen in an expression that need to be evaluated. And those also will have to have some sort of order in which they're evaluated. And my camera just did something funny where it turned off for a second, but I think we're good. Yeah. So this is not going great for first stream, but I guess it's not going terrible. So let's keep on going. So what we have here right now is we have this REPL, this interpreter, this interactive environment in which we're able to uh, type in statements, and we're able to turn those statements into tokens, and then we're able to take those tokens and in turn create a data structure to represent what we want the computer to actually do, which is called an abstract syntax tree. At some point of time, we were also able to evaluate an expression here. But when I introduced this other concept of a statement, and a statement is slightly different than an expression, and also I introduced the concept of blocks, which are blocks of statements. And we'll get into more of what all those things mean, and they can mean something slightly different depending on the language and how things are defined. But you can see here that this actually is correct syntax, and this is because our current version of this environment supports, or kind of partially supports, blocks of statements. So you're able to give it a begin, and that tells it, hey, begin a block. And this is very similar if you have used other programming languages like JavaScript or C, or any of the languages that use curly brackets. This is similar to opening curly bracket and closing curly bracket, and that's a scope or a block, or however you want to, or a compound statement. Again, depends on the terminology of the language what those things are called, but they all represent a very similar concept, which is a group of statements. And you can do different things with those statements, right? Like when we're talking about, for example, loops, you can have a loop, which is a condition to tell the the language to execute a statement a number of times or until some condition is done. And that statement very often is actually multiple statements, so it's a compound statement, right? It's a block of statements to execute. So this is why having a way to define compound statements or blocks is useful in programming languages, because this is how we can define if blocks for if statements, for conditional statements, or else statements in the conditional statements, or loops for any of those other things. Um, and then when we're talking about memory management and other and stack operations and things like that, uh, blocks also in a lot of languages end up being identical to scopes. And this is something that I guess we're not even probably going to get into now because now we're really going down the rabbit hole, and we should probably uh, stop looking at this example of what exists. Just know that we'll put it up on GitHub and it will be there for people to look at. We'll leave it in this broken state. The reason why it's broken is that we've only partially implemented its ability to. It can only really evaluate expressions right now, but we allowed it. We've developed it enough where we can actually define statements and blocks of statements, compound statements, and now the interpreter doesn't know what to do with them, right? We don't have any kind of functionality to interpret that, and also some of the uh, functionality that we have to show uh, what the interpreter has created as far as data structures is also broken because that was only implemented as far as like showing expressions, but I've went a little bit further ahead. So now we need to catch all of that functionality up so that we have ways to like debug our work and continue developing this. But we're probably not going to do this today because this is already taking way longer than I was expecting, and I haven't even really gotten into the well, I've gotten into a lot of yapping already, but I don't know how much useful yapping I've gotten into. So, uh, yeah, so we'll get out of this and we'll take a look at some programming language basics. Or I guess we can start with some classical computer basics. And what do I mean by classical computing? Well, classical computing refers to essentially pretty much all the computation devices that are around us, at least on a day-to-day basis, uh, like cell phones or your laptop or mainframe computers or servers or whatever it is, right? Anything that pretty much runs in a CPU, memory, and like a disk drive or something like this can be considered a classical computer, um, as opposed to stuff like mechanical computers, which have existed in history, right? And people still build mechanical computers that uh, can perform computations, right? Because that's what a computer is. It's a device that can perform computations. Now, computer in our modern day and age has started to really be associated with what uh, classical computers or computers that are most widely used now are used for, which is general computation, meaning that they can do a lot more than just some specific computation, right? But like you could play video games on them, you can browse the internet, you can do all of those things, but ultimately all of that ends up being some form of computation, right? Like information processing. Um, but there's also like quantum computers, and quantum computers, if the people that, and this is way out of my way out of my realm of expertise or even really fully understanding, but in theory, if quantum computers actually end up working the way that people that are designing them want them to work, they could be much more efficient in representing certain specific kind of computations than you can represent in classical computers, and that has to do with just that the kind of physics that happen in quantum computers can represent or um, be a substitute for, not necessarily a substitute for, they're a good representation, they're a good way to calculate specific kinds of computation that are very hard to compute on classical computers, right? But if quantum computers end up working the way that the people that are working on them want them to work, like in theory, they're able to potentially represent these kinds of computations that are like infeasible to do on classical computers. But the kind of physics that take place on the quantum chips can represent those calculations in a way that it is feasible and they can be calculated. Yeah, now we're really kind of on a different topic, but the whole, I guess, point that I'm trying to make here is that what we're talking about here is computers as we know them right now in their modern form, the way that they're utilizing all the devices around you, right? Outside of some edge case, unless you work on quantum computers, but then you probably don't need me to tell you about classical computers. So the way that these machines work in general is that they have a central processing unit, right? A CPU. Um, and we'll draw a box here with our CPU. And we can think of the CPU as a magic box. And what this magic box can do is it can take a number, perform an operation on that number, and then output another number, right? So it is numbers in and numbers out. Everything that happens in computers happens with just numbers. Computer graphics, all of the text that you see on the screen, right? Like the all the dudes running around in Call of Duty or whatever, and their guns and bullets and everything else is represented in only numbers, right? So that's the only thing that a computer can perform operations on, specifically a CPU, right? A central processing unit. That central processing unit can take these numbers in and it can output new numbers out by performing operations of those numbers, combining them in certain ways. Obviously, the basic way to think about this is that you can think of mathematical operations, but it can also do logical operations, like you can compare two numbers. You can say, hey, is this number bigger than this number? It can make logical operations like or and and that are the mathematical logic operations. But it's essentially limited to just those things, right? And you can also move these numbers around in memory, right? So, well, how does that effectively end up being anything interesting outside of it just, I don't know, calculating uh, whatever your grocery bill or something like this, right? Well, the idea is that you can connect devices to these computers, right? Like so, the numbers that are coming in here don't have to come in from one place, right? They can come in, for example, from memory, right? Which is something that um, all classical computers have. They have some sort of form of memory where they can store these numbers, right? And the processor can move these numbers around in memory. So you can take a number from, let's say, like uh, this spot in memory and move it to this spot. I don't know if you guys can see like the cursor that I'm. It's kind of a weird color, but let's say like this is a block of memory here. You can read it and you can just move it here, right? Or you can read these two blocks of memory that, let's say, have the numbers 1 and 1, and then you can go back here and store the number 2. So you can add those numbers. You can read this one from this part in memory. You can read this one from this part in memory. You can perform the plus operation, and then you can store this back into memory here, right? So that's one thing that the computer can do. But how can you, like, what does that mean and how can you see it? Well, you can also interact with things like other devices, and those devices can be things like a video card, and this video card then in turn, this is not working very well, but there you go. So we'll say that this is our display or monitor, and this is our video card device. Probably not how we spell device, but that's okay. You can forgive me my misspellings. I'm originally from the parts of Eastern Europe, so even though I've lived in an English-speaking country for a long time, um, so the CPU can also write numbers to other devices. In this case, we have this very specific device that's a video card, and this video card can then interpret those numbers to mean what images to display on a computer monitor or a screen or a TV. Another thing that, right, like another device that we can interact with is something like a network card, right? A network card device. So a network card, as I'm sure you can figure out by the name, is something that can communicate with a computer network. It's a way that the two computers can communicate with each other over long distances. And this is kind of the basis of the internet. There's a lot more there, a lot more devices in between. But all of those devices, all they're doing is they're taking in numbers and they're either interpreting those numbers in some way or just passing those numbers along to some other devices, right? And the way that you're able to browse the internet is that this CPU, the core of the computer, is able to run a program, and the program is also stored in memory. So I guess this is like a critical thing to say is that how does the CPU know which operation to do? Well, in the same way that we're storing one in some memory location and another number, in this case one in another memory location, there's also a memory location where we're storing what operation the CPU should do, right? So a program that a computer can understand is a bunch of numbers that are in memory, and those numbers mean something specific to the computer, like which operation it should do next. And it's a literal list of operations. So if this was like doing operations plus, minus, multiply, whatever, those would be represented in memory one after another, where the CPU would be reading the instruction. This is what those operations are actually called. On the terminology is it's a CPU instruction because it instructs the CPU, this processing unit, on what operation it should do, and those operations can work on um, the numbers they can, like where they get the numbers from can vary, right? So, and again, to keep this kind of shorter, we don't want to get too far into it, but there's different places where the CPU can store uh, data or numbers in. Like it also has tiny little memory blocks inside the CPU, which are called registers. And this is commonly where a lot of the work is done. It has access to this bigger block of memory, which is your RAM in your computer. Um, it also has caches and things like that to make things faster, but we'll just like skip all of this. The point is that the CPU is like, let's imagine some very simplified version of this. It's always reading, hey, like it starts here and it says, I'm going to do an operation. And it says this operation is plus, and then it also based on how the operation is, what number is in that, or like it could be actually multiple numbers that define the operation. It could tell it where to read the other numbers that it actually needs to operate on, right? The operands, right? So if the operation is plus, it also needs to know uh, where are the numbers that it needs to add together, that it needs to plus, right? And those can again come into different places, but let's just imagine they're somewhere in memory, and there's that's just part of the magic that happens in this for right now. At some point in time, we could take a look at our at the Snake Toy virtual machine and have a stream on that and get into a little more detail, because I feel like I'm already going into too much detail here when I want to kind of get into a little bit more detail about programming languages. But I guess we sort of had to cover a little bit of this. Um, yeah, so the idea is that a modern computer is just a CPU with memory and a bunch of these other devices, right? And another one of these devices can be something like a hard disk. Uh, Obviously, nowadays, uh, well, whatever. We won't get into why it's called a hard disk, but some sort of other, like the computer memory in general, right? When you turn off the computer, that gets erased, and that's why like when you turn your computer back on, it might take a while for the operating system to load, although with newer technology that has changed. But again, we can get into that if anybody is interested, I guess, at some other point of time. um, the point here is that you have this central processing unit that the only thing that it can do is it can do operations, and those are mathematical and logical operations and some other ones on numbers, and it has access to memory where it stores those numbers. And some of those numbers are actually the numbers that tell it what operation to do, and some of those numbers are the data or the operands or whatever you want to call them, the numbers on which it needs to do those operations, right? And then you can move them around in memory, and then eventually you can also put those numbers out to other devices, not just memory, and those devices can then decide what those numbers mean, right? So you can actually send those numbers across the network using network cards, and you can then display graphics on a graphical screen or text on a text screen, um, even though that's not a thing anymore, but it used to be back in the day, or even print things on a paper page with a printer, right? So the printer is just another device through which the computer can, uh, to which the computer, the CPU can interact with, right? And also, obviously, there's ways in which you can give input to the computer. For example, I'm moving the cursor here using a mouse, and also I'm able to type, which I do with a keyboard. And those are just input devices. But ultimately, everything that those input devices do, right, like this cursor, its position, and everything else gets translated to numbers that are stored somewhere in memory, and the CPU can do operations on them, right? And then it can, uh, there's a program in there that's doing complex processing to actually display this cursor on the screen. So it's reading stuff, it's reading numbers from the mouse to know where the mouse is. There's a bunch of processing that happens, a bunch of instructions, a bunch of operations, additions and multiplications and subtractions, and a bunch of other nonsense happens in the CPU. And then it finally writes out some magic numbers to the video card, and the video card writes uh, uh, paints this picture of this cursor on the screen, right? Like this is all that's happening uh, millions, billions times a second, depending on how fast your uh, CPU is, so that every time I move the mouse, this cursor can move, right? But this is all happening repeatedly over and over and over, along with everything else. Like it needs to draw all of these buttons on this browser window, and it needs to send things to the networking. Like I'm currently on a website, but this website has a way for me to interactively draw on the website using ASCII characters. These are all things that have to go through the CPU and the network card and the graphics card and a bunch of other devices in this computer. And repeatedly, the CPU needs to process a bunch of information, a bunch of numbers, and then write those other numbers into these other devices and back and forth, so that all of this that I'm showing here is happening, right? Me being streamed to Twitch and YouTube is also a bunch of numbers that are being processed by the video card and the CPU and a bunch of and being passed along between memory and a bunch of other devices and the network, so that my face can be on your screen, or in this case probably nobody, because I'm sure nobody's actually watching this currently, but we'll pretend like you guys are watching it, and maybe someday you will. So that's how computers work. But if you've ever seen any kind of programming languages, you likely know that um, you are not typing numbers to interact with a computer, right? Like, um, I suppose we can show like uh, Python code example. Come on, Google. Okay, and for some reason, are we going to? There we go. And now here, right? So like, it looks much more like human language, right? It's using in kind of English words, and looks like kind of like regular human writing, not quite, but it doesn't look like a bunch of numbers. That, I mean, you can write numbers in there, but that you're not just writing a sequence of numbers that are somehow magically telling the computer what to do. Well, the reality is the computer doesn't know how to execute a program like this at all. It only knows operations and numbers, like we said. So there needs to be another program that actually translates all of these words down to numbers that are the instructions, the operations that the computer needs to do, and the data that it needs to do it on, right? So a programming language is, or so we can get a little pedantic here, right? It's the implementation of a programming language is a program that takes text written in a text file and translates that text to numbers that are the operations the computer needs to execute. Those numbers are generally referred to as machine code, right? It's machine code because it's the code that tells the machine what to do. Um, So if you've ever looked at an executable file, whether it's on Linux or Mac OS or an exe on a Windows machine, and you open it up with a regular text editor, it looks like a bunch of nonsense. It's a bunch of symbols that are not like human readable text. And sometimes you can even make the computer, like if you print it to a terminal, make funny noises or something like that. That's because that file is really meant for the computer to execute, and the meaning of that file is the machine code and the data that needs to be loaded in memory, and then the CPU can be pointed to where the numbers that tell it what to do start, and it can then start sequentially executing them and reading from the places in memory to grab the data that it needs to operate and perform those operations and do all of those other magical interactions with devices and everything else that we talked about. But even the most complex things you see it being happening on a computer happen based on that they're all um, emergent, right? Like all the complexity is emergent. The things that a CPU can do are super basic, right? It can take two numbers and add them. It can decide if two numbers are bigger or not. It can read a memory from this location and write it to this location. Uh, it can, I suppose we can, let's see, what's a good way to represent this? I probably should have done a a little bit more planning here, but that's all right. We'll keep going since nobody's probably watching this. And, at some point, maybe we'll even delete the video. So if we imagine this is memory and computer memory, right? And here we have 10, and here we have 20, well, 30, 40. These are the locations in memory. These are not the values in memory, right? Just imagine this as like a list of locations. In each location, I probably should have made this box slightly smaller. So let's do this like that. All right, so each location can have a 4-digit number in it, right? So and the CPU is reading all of this, right? So we'll just do our CPU here again. Boom. All right. So the CPU is going to start executing. It's going to start reading, like you tell it, and we won't get into how you tell it, but there's a way you can tell it, the central processing unit, where in memory should it start reading the program it should execute. So in this case, we'll tell it, hey, like start executing at location 10, and then it's going to read whatever numbers written here, and we're just going to like write like some, oh, this was a little too many numbers, that's not what we wanted, right? Like totally screwing this up. Well, we want it to be different number, right? So don't worry about what's in the numbers are. Like doesn't matter. Like that changes with computer architecture and the different processors and so on. The point is this is the machine code. These are the instructions that are telling the CPU what to do, right? Let's say that over here we have the data. So here we have 1 and 1, right? And let's say that this first instruction tells it, hey, add two numbers, and I don't know, like we'll say that this is location in memory. What are we at? We're at 40. I don't know. We'll call this like 90 and 91. I know this is not very consistent, but whatever. Uh, so we'll say that at location 90, like this is where the data is being stored in memory. We have the number 1. At location 91, we have another number 1 being stored. And let's say that this first uh, number here, well, is, I don't know, let's call it 999, right? And let's say that to this CPU, the number 999 means add two numbers together at locations 90 and 91. Now, the in real CPUs, it's the way that you tell it where the numbers are located is a little more sophisticated than just always assuming the numbers in location 90 and 91. But we're just going to go with a super simplistic use case just to illustrate this point real quick, because this is already, I think, taking a little too long. And So now the CPU, we've told it again with another magic instruction. We won't get into how that happens at some point of time. Maybe we'll, when we look at our virtual machine, because that will be a good way to like show how these things are represented and how we can emulate them. But somehow magically we told the CPU, hey, start executing in location 10. It's going to read 99, then it's going to realize, hey, this is the magic instruction that tells me to add two numbers together, right? And the instruction, again, let's make it super magical, and we'll say that it's read the numbers at 90, at location 90 and location 91, and then store the result in location 92, right? So it's going to read this instruction. It's going to say, okay, I need the numbers at 90 and 91. It's going to fetch those numbers. That's what the terminology is for when the CPU is grabbing data from memory. It's, or instructions also. It's fetching. So it's going to grab this. It's in its internal memory. That's kind of hard to say, especially for somebody who's not a English speaker. It's really hard for anybody. Anyway, so it fetches, right, these two numbers. It performs the operation because it knows what operation to perform, because it first fetched this 999 number from this magic location 10 where it started executing from. It's going to then write the result, which in this case would be 2, to again this magic location that the instruction it's telling it to do so. In our case, we're hard coding it, but there's ways the instructions actually tell the CPU where it should read the memory to and where to write it to. And sometimes it takes multiple instructions to do that. Again, we're not going to get more into that. And then it's going to move on to the next instruction. And then it's going to perform some operation and do something and move on to the next instruction. And then it's going to move on to the next instruction, right? But sometimes you might want to go back to executing code somewhere here, right? And that's another operation that the CPU can do, is it can say, hey, like, check a certain condition. Is this number bigger than some other number? If it is bigger, then go back to, like, let's say we're at location 40, go back to location 20, right? Those are called conditional jumps as an instruction. But again, that's not super important. It's just important to know that, like, that's something that the CPU can do, right? But all of those things, as you can see, are very simple. They're very, like, small atomic operations, super simplistic, right? And it would be very hard to write a sophisticated computer program with just those instructions, right? Now imagine having to represent those instructions as numbers and remember all the numbers of what the you know, which instruction each number means and what it tells the computer. And depending on the architecture, you can have hundreds, you know, on hundreds of instructions that a CPU is able to execute. So how can you memorize those? Well, the first thing that really people came up with, and by the way, historically, the first computers were actually programmed in this way, where you just wrote the numbers in memory. And the way that you actually even wrote the numbers was by literally flipping switches or moving cables around and so on. Yeah, I guess we won't get into too much of the historic context of computers, even though that's very interesting, and maybe we'll do a stream on that at some point in time too and yap about that because it's interesting. But eventually people, you know, got tired of doing this kinds of thing, and also keyboards were kind of, you know, invented, so you're able to type in like human language symbols, and there was a way to connect those and translate it down to numbers in the computer, right? You had like a keyboard that functioned, and the computer was able to interpret what you're typing in there and somehow put it in memory with some other programs. All of this to say, even then, some programs were written in machine code, meaning that people literally knew what numbers to type in, and they typed them in memory, and then executed that code, and the computer did the thing, right? So, like the Apple I, the first Apple computer, had something that Steve Wozniak made a program for it that he booted into, which was the Wozniak monitor, Wozman, and what that allowed you to do is just edit memory and use your keyboard and type in numbers in memory, right? So you can jump around in memory edit those numbers in memory, and then you can tell the computer to then execute at some point in memory, right? Like, so you could tell it, hey, start executing at location 10, and you previously had typed in the set of instructions, the numbers in memory that you wanted to execute it. And literally, this is how people were programming. At some point of time, that became a little infeasible, especially for people that were trying to do complex, important things, right? Like real stuff was being done on computers that mattered, and the first solution for that was to uh, just create a simple program that you can type in some sort of English sounding word that just translated to the instruction the CPU should execute, right? So like we have this instruction, the number for it that the computer knows how to interpret is the number 999, but let's say that you had something like add, right? And as opposed to you having to remember that 9999 is the add instruction, you're able to just remember, hey, like I can have a text file. In that text file, I can write English or some sort of, it doesn't have to be English, but you just happen to historically, uh, a lot of stuff is in English because this is where a lot of modern computers were developed, is in the United States, uh, English speaking country, and also previously Great Britain, another English speaking country. So a lot of historic momentum there for English being kind of uh, the computer's first human language, natural language that they were designed around. So you can have a text file that can have a bunch of these instructions like add, subtract, for example, move some like the number move the number 3 to location 10, or let's say like 90, let's say location 90 because 10 is our program, blah blah blah, right? Or like you can jump to, let's say, location 30, right? That doesn't matter. The point is that like people came up with like assemblers or assembly languages, which are a way to make writing computer programs slightly friendlier, right? And assemblers gave you this set of human readable words, kind of, right? They were still mostly like 3 and 4 letters or 5 letters, but there were as instruction mnemonics, right? So they're like a way to, they're a mnemonic device. They're a way to remember how the numbers that you need to tell the computer, or rather that you don't need to remember the number that the instruction, uh, that the specific instruction or operation uh, represents, but you could just remember these kinds of words and then write them in a text file, and then you had a program that just took those words, this text, and then translated it into the numbers that then tell the computers which operations to uh, perform. And you can then load and that was like a assembling, like you use the assembler to assemble the file. There's a little more to it. There's also linkers and things like this, but I guess we'll get into that at some point in time. Either way, you ended up with a file with just numbers, and then you were able to, through the operating systems or other ways back in the day, load that file into memory and then start executing that. And that also assemblers then started giving you convenient ways to also package some data, right? Some numbers or text strings or other things like that in your text file, so that if you wanted to display like hello world on the screen or something like this, you didn't have to like manually like patch in those numbers in there. Like as the numbers, you're able to like, you know, give it a specific like some other set of like short English word and say, hey, I want to define the numbers that would represent the text hello world at this location in memory. And then they give you some other convenient ways to like represent, as opposed to you having to always refer to locations in memory, like, hey, this is location 10, this is location 100. uh, they give you a way to add human readable labels to certain places in this text program, and then the assembler will translate that to the appropriate memory locations when it compiles stuff, and also when the program is being loaded into memory. uh, yeah, so that's a lot of yapping for, I guess, what is our first technically programming language, but really it's the first assembler. or the first solution to this problem of like the to get a computer to do anything, even a simple thing, takes a lot of these instructions because these instructions are so simple, and it's a lot to keep in your mind. So like there needs to be a better solution, and that was the first solution, right? But once you started in this path, then you could be like, well, the, like we want to represent much more complex things than just a few subtractions and additions here. Even this mnemonic representation, these assembly languages, are kind of difficult to represent something very complex on, or to structure a very large and complex program. And this is where, like, a lot of like the researching, like the 50s, 60s, 70s, 80s, even into the 90s, even to these days, there's new programming languages that are being invented, right? Like Rust is fairly modern language. You have things like Jonathan Blow working on Jai, or right, like so. Program language development has not stopped even in the day and age of large language models, right? Like we're in the future now, and there's still plenty of uh, new computer programming languages being developed because uh, we're depending on computers more and more, and the things that we want computers to do have become increasingly more and more and more and more sophisticated. So we need better and better solutions, and there's a whole argument of which these are actually better solutions and which are not, which are dead ends of evolution, so to speak. But we're not going to get into uh, the language wars or any kind of controversies, at least not for now. We're just here to have fun and learn a little bit about programming languages. So what's the next thing that you can do? Well, you already have a program that you've created that can take um, human text. You can take text written in a computer text file and translate it to machine instructions, right? Like even though it's a very basic version, you're essentially still writing out just the machine instructions in the text file, just in a slightly different way. You're not writing the numbers, you're writing this mnemonics, but it's still very close to what machine language is. Well, can we implement a program that does something a little bit better? Can we write something that sounds a lot more like human language in a text file and then have the computer translate it to these magic instructions that he knows how to execute, right? And that's how a lot of the first computer languages started. They attempted to mimic, and to this day, there's still some of that goes on. They attempt to mimic natural languages, right? So actually, a lot of the really, I guess, academic-y computer language development stuff was tightly linked with the linguistic developments, like throughout the, I think, like 50s, 60s, whatever. A lot of progress was being made in like linguistics and an understanding of how human languages were developed and what that meant, and like how do we represent symbols and what does that mean for like actual human cognition. And a lot of those things ended up being like, as always in computer science, uh, sort of computer science absorbs all the other sciences into them in one way or another, because ultimately computers are just computational devices that can perform also a lot of outside of playing video games. Apparently you can do a lot of helpful scientific stuff on them. Who knew, right? So anyway, all of those things were kind of developing at the same time, and I think probably the first successful or semi-successful uh, computer language that stepped away from writing machine code or writing assembly code was Fortran, right? Developed in IBM, and that I think it states for like formula translation or something like this, right? Because the whole idea was that like they wanted you to be able to write like stuff that looks, like what we started with earlier in our stream: 1 + 1 times 8, divided by 7, and then like maybe we want to like square root like this whole thing. Let's see, SQRT. That's I think I'm missing a paren here, but you get what I'm trying to say, right? Like the idea being here is that you want to write like expressions that look a lot more like mathematical expressions, the way that you're used to doing math on paper, and the computer, and this would be then translated to machine code for the computer to interpret it, right? Um, but also you wanted to do other things. You wanted to read data from, let's say, a file on disk, right? And you wanted to read a bunch of numbers and then perform this formula on them, right? Like, uh, in some of these most basic, like initial use cases for computers, right? Like if you wanted to batch process a bunch of accounting files, right? You wanted to describe how that happened. It would be much easier to like describe like some sort of like financial formula, like in this mathematical language, and also like say something like, uh, I don't know, like loads. And I'm just making stuff up here because I don't know Fortran, but like the idea was like you could say something like load file uh, taxes.txt, right? Or like read from the database or something, and then like perform this operation on each line in the file, right? So like you can say uh, for line in lines, and I'm reverting to like Python over here, right? Like do this formula, right? And Fortran wasn't quite as friendly as like something like Python or like the modern languages that we know. There was a lot more, um, a lot stricter uh, syntax and expectations of how to structure things. But that's because it was invented when computers were still uh, working with much more rudimentary forms of storing data and representing data. There's things like punch tapes and punch cards, and again, we can get into some of the history maybe at a different stream because it is very interesting. But the point is that Fortran looks very archaic to us nowadays, but it's still around because a lot of code and a lot of like very fundamental like scientific library code and like a lot of early super useful code was written in Fortran. So and I think you could to this day still like cross compile Fortran to a bunch of operating systems. There's plenty of like working compilers and things like this. So I think there's a lot of legacy code on mainframes and other like big important machines that's probably still running Fortran. But I think also uh, potentially a lot of like fundamental code that other languages like even C potentially maybe are using certain libraries maybe still exists as Fortran code from what I understand. But the point is that this was a version of uh, a way to represent a program that was much closer to what a human can naturally understand, much more closer to the human language, right? But now you needed a more complicated program to take that language in the text file and translate it into a program you can run on the computer, right? Like, whereas an assembly program file is pretty much a one-to-one mapping of the instructions, right? Like it's just that the instructions are not numbers but they're words, right? And there's a little more complication as assemblers like over the years have gotten more and more uh, futureful, so they have much more complicated, not complicated, but much more powerful things that you can do with assemblers. There's macro assemblers and things like that. Anyway, keep getting myself distracted. But the point is that there's still a even the most modern assemblers is still a more or less a mapping to machine code and what the structure of the program might look like in memory versus what a high level language program would look like. However, a high level language program allows you to be much more expressive. It allows you to think a lot less about what's happening in the computer and a lot more about the problem that you're solving, right? And again, we're not going to go down this path yet, but there is uh, even to this day, with as powerful as computers are and everything else, a lot of what the job of software engineering is to be able to draw the line of how concerned are you with what's happening with the computer versus solving the high level problem, and the ability to balance those two things against the kind of performance that you need, timetables in which things need to be implemented by, right? Like the timetables of businesses, and right, because these things are obviously like unlike recreational programming where I can just sit here and yap, you know uh, like everything else in human endeavors uh, tends to have economic implications and so on. But anyway, I guess I'm going off track again a little bit, but I think it's important to note that uh, even to this day, again, in the modern day and age, the people who are really capable software engineers are still the software engineers that truly understand what happens at every level of the machine to some degree. But uh, the higher level languages, especially if they're good languages, give you the let's not put labels like good languages, I guess, on them, but like if like all tools, right? Majority of the time, it's about the use case and where things fit. But what I'm trying to say is that um, languages that are very expressive and allow you a lot of control, but that are also with that control. Let me let me rewind this. So the idea behind the high level languages is that they should allow you to express a problem that you're working on in a way that it's closer to the problem that you're attempting to solve than to what has to happen internally in the machine. However, even to this day, very often to write good software, you need to have some control or understanding or some facilities in the high level language to control some of what happens in the machine, right? That has changed from the days where you had to write super optimized machine code by hand. Now you have compilers that can write, generate a much more performant machine code than uh, humans can. But there's still cases in which understanding cannot be replaced, and we can at some point of time. Maybe I'll have a stream where I just go off on what really software engineering is about, tangent, but let's stay away from that right now because we've already gone into too many tangents. Um, but yeah, so high level languages, right, like Python, like you're able to express something like this. You have a shirt color, you're able to say, hey, the shirt color is the text red, and you're able to say, hey, is the shirt color red, and say something. If it's not red, then say something else, right? Having to express this in assembly instructions or machine code instructions would be a much more arduous task. Uh, for something like this, not that much more arduous, right? It's not like to write this example in assembly code wouldn't be that much crazier and more difficult. And actually, maybe we can just yeah, let's let's work with the robots here, um, and just tell it to show this in uh, let's say 65 assembly. So let's see let's see how good the language models are. Essentially, now I'm asking. Looks like the response. Oh, interesting. Yeah, so I guess he decided not to give us this answer. Well, this is supposed to be more illustrative, but uh, maybe it's because I asked it to rewrite it in like a very old school assembly. There we go. So this is probably, this looks maybe about correct. It's actually probably using some newer 8086 instructions that I'm not familiar with. This is like Intel instructions essentially. Um, but yeah, you would look similar to this kinds of to this kind of thing, right? So like you have to think about much more here and to write this than if you remember what our initial example was, which is just these statements, right? These you have this the declaration of the variable with the color red inside it, and then the check to see if the color is this, and then printing. As you can see in assembly language, you have to be much more explicit. Here we're declaring like the strings that we need to print as opposed to being able to just print them in line where we're saying, hey, print this string in quotes. We have to like decide, hey, like this is telling it, put this string somewhere in memory. And the assembler is also being very helpful here because it's actually helping us find where this locate this first in memory. We don't have to give it a specific memory location, but we still have to like give it this whole like data section and declare it here like this, and then we're doing like some funky address mathematics right here. It's really not that funky if you programmed in assembly, but you haven't, then it probably looks kind of weird, especially compared to just like being able to say print, right? Like this gets the length of like this string right here. And here you like notice there's this number 10. Like, what the heck is this number 10? Well, this is actually the new line, right? Like the new line character that normally you would represent like in Python or something like this, right? You know, much a ton of modern languages you would escape it as slash n, right? Well, in reality, that's the number 10 in memory, and here this is what you're writing. Like when you print something on the screen in the terminal won't go to a new line, and you've maybe even seen this if you've done like a hello world or something, you forgot the slash n, and then your prompt becomes like just concatenated to what you printed. I'm doing funny stuff with my hands here that it's supposed to represent that, but not in the camera. I think you know what I mean. Like they're connected as opposed to the prompt going to the next line, and that's because like this 10 is missing or the slash n. So like everything is just much more explicit, and then we're doing all of these move instructions that are moving things between like register, which is like the internal CPU memory and memory, and doing a bunch of other like magic. This like jump here, this is essentially the if statement, like this compare uh, statement, and this jump. This is effectively like that uh, if the string is equal to red, right? Like this is effectively uh, this check. It's actually, if you're comparing like a longer string, this would actually be much more complex. And I'm not even sure if this actually would be absolutely correct. That's again now the important part. I would have to actually like read this for a second and just make sure that like it's doing things, because normally the string is actually represented as many numbers in memory. So theoretically, like you really have to compare every number to every number to make sure that two strings really match here. This is doing, I think, some sort of optimization just because I think maybe because like the word red is only uh, byte by byte while equal. Also, maybe this is jump if not equal, print else. Yeah, again, doesn't matter. The important part is that even this like equal statement is actually a much more complex thing. And then when we have to actually print something to the screen, we have to do this all of this loading of stuff in memory and then do it. Like you notice this instruction is called syscall. That's because it's calling into the operating system, and it's asking, hey, operating system, display this string on the screen for me, right? All of these things are hidden by a higher level language, right? Some higher level languages give you access where you can make syscalls directly and uh, like ask the operating system to do things for you and so on. But even that would be in a much more friendlier way than having to load things into this like registers again, which this is the internal memory of the CPU, and create all of these specifications. Or obviously, majority of programming languages give you a lot of facilities. For example, right, like the whole idea behind Python having batteries included is that like it comes already with a giant standard library with that can do just about anything you can think of. And then if you can't find that, there's other packages that have been written that can do that stuff. So like if you want to print something to the screen, you don't have to do a syscall. You could just do print, and you don't have to like define a bunch of stuff. Like all of this like magic here can be done for you, right? But ultimately, that still has to get translated to assembly, or really not even assembly, because this is still not what the computer is executing. This is assembly, but realistically, this still needs to be assembled. Would really the high level language needs to be represent like transition into or represent like the representation that it needs to be converted into is a bunch of numbers that can be loaded in memory, and that's the only thing that the computer can execute and understand, right? Or the CPU. Okay, so uh, I guess this is maybe a good stopping point, even though we didn't exactly get into uh, the actual stuff that I wanted to cover about programming languages. I sort of left it at, I got a little too much into how uh, CPUs work and a bunch of other tangents and assembly language and machine codes and so on. But I guess maybe uh, this could be stream one, and then we could get into stream two where we yap about how something like this or Python or whatever is translated down to machine instructions. And there's multiple steps, and we'll get into like the higher level idea of those steps, and then we can get back and look at the code and see how like each one of those steps or potential way, because there's many different ways you can implement these kinds of things. But look at like one implementation, the one that we're working on here in Python, that hopefully will be slightly easier to understand, maybe, I don't know, of how like a bunch of strings, a bunch of text in a file can be converted into machine instructions for a computer to execute. And we'll get into the high level steps, and then we can get into the details of each step, and we can jump between the code, and then at some point of time we can even start making modifications to this thing that exists. And yeah, but for right now, I guess what I can do is we can just put this stuff up on GitHub, and then I'll add those links to the video. Hopefully there's a video. I haven't actually checked. I have not actually peeked at how, if our stream continued streaming correctly to YouTube and everything else. Everything looked good in OBS, so hopefully there is a stream and a video that we can list here. So yeah, we'll call it here for, well, let's push this up, and then we'll call it here for stream one. And as awkward and as awkward as and not as intended this came out to be, we'll leave it up there, and maybe this could be a start to something that we do occasionally, every week or every other week or something like this. So we'll just say first, and we'll push this up to the repo, and then we'll go from there. I guess this will be it for now, and yeah, hopefully we'll see you soon in the next stream that will